I want to talk to you about size.
Who been talking to you?
Let me finish the sentence. Size and life.
Oh, okay, good. Because, I'm just saying.
There's much more conversation that could be had on that subject in this world.
Really?
Because physics matters in it, but typically when people talk about life, they only think of biology.
Of course.
Or at most, chemistry.
I like the chemistry.
Physics is the substrate of it all.
You would say that,
No,
though.
stop.
Let's be honest.
I'm just telling you.
Yeah.
Okay? So let's start with some basic facts.
Okay.
All right? When you're growing up, especially if you were a boy, they say, how strong are you? They would challenge you to this. And you would show them your muscle.
Yeah.
Let me see
the gun show, baby.
Let me see the bicep.
Welcome to the gun show.
Okay?
Yeah.
What they're measuring is the cross-sectional area of your muscle. So the bigger the muscle,
the stronger
it is.
Unless you are Bruce Lee. A double scribble.
So you need to know, however, that as your muscles get bigger, they become heavier. It becomes heavier according to the volume of the muscle, but the strength increases only as the cross-section of the muscle.
I don't understand what you're saying.
Think about very heavy animals have very thick limbs. You need thick limbs to hold up that much weight.
Right. Okay. That makes sense.
Got that? All right. As you get smaller and smaller, you don't need thick limbs. How thick is an insect leg?
Yeah, not thick.
Right. It's not. The ant picks up something that weighs as much as it does.
Right.
And walks around with it. The smaller you are, the even less you weigh for how small you are. Because weight scales as your volume. Weight scales as your radius cubed, but your strength scales as radius squared, which is basically your cross-section. This difference means as the animal gets larger, its weight outstrips the ability of its strength to hold up its body. So it needs really, really fat legs to compensate.
Gotcha.
As you get smaller, the weight starts going away fast because now the radius is getting smaller and smaller, and then the area basically wins because now your volume gets smaller faster than the cross-sectional area gets. So try this, right? If your radius is 2, then your volume goes as radius cubed. So what is 2 times 2 times 2?
That's
you get what?
8.
8. Okay. Now if your radius is a half,
oh, it's going down.
it's going What's a half times a half times a half?
Right.
That's an eighth.
Right.
Okay? So you get this crossover point in the animal kingdom. That's how the smaller the creature, the bigger is the weight it can carry.
That's wild.
Relative to its own body weight.
That's amazing.
And the higher it can jump.
Right.
Because its body mass isn't much relative to what the legs are.
Which is the creepiest thing in the world when you see a kangaroo mouse.
Oh,
it's a tiny little mouse and it can jump like 6 feet. I'm like, no.
Or a flea, which is, barely the size
barely
of thing.
visible.
And then they count how high above its height it can jump.
Right.
And it's 10 times its height or something, 20, 30, whatever is that number.
Right.
You ain't jumping that high above your height.
Never.
And neither is any other large macroscopic object. The laws of physics are dictating what your acrobatic skills will be depending on your size.
The universe is a perfect 4D sphere. You would see your past location, in your case, a young solar system, from every angle, so it would appear smeared out across the cosmic horizon.
So I don't know if I can answer it in the precision that
he's talking
here,
about, right?
But I can tell you that we do live in an open universe, which means we're expanding out forever.
Right.
So there is no sight line that will come back to where we are.
Right.
It goes out.
Because the sight line is continually moving.
Correct. And out away from us.
And out away from us, so there's no way that you could loop back because it's always going.
In a closed universe, the universe will recollapse so that a sight line, in principle, will ultimately come back. And the way to think about that is just the surface of a sphere.
Right.
We'll call it a balloon, a perfect spherical balloon. We're all crawling around on the surface of that balloon, and if you send out a beam of light, it will go away from you, but then come back and hit you in the back of the head.
Right.
Right. But that would be later.
Right.
Okay. And as the balloon begins to shrink, well, it wouldn't have to shrink. It just has to be closed. But if it's closed, it will shrink.
Don't look at me. I'm not the astrophysicist.
So the cosmic microwave background,
Right.
we have done some experiments to test for this.
Oh.
So the microwave background is in every direction.
Right.
So if you look this way and you get I know exactly the patterning that's happening there. And then you just look that
Turn
way.
around. Right.
Is that exact pattern?
Same pattern.
Because if that's the thing, then that means they are the same place.
Right.
That means that was a line that went around and met on the other side.
Right.
Okay? We haven't found that.
We haven't?
No. But we've looked.
We've
is
looked.
my point.
Gotcha.
We've looked very carefully for statistically significant repeated patterns
Gotcha.
all throughout the cosmic microwave.
Gotcha. Okay.
Yeah.
Okay.
So that's the best I can answer that.
No, that's a great
But
answer.
Jana might have come in with some more teeth in that answer.
Well, leave it to Jana.
So this is not the first time we've seen an announcement of biomarkers indicating the possible existence of life. So it's not the detection of life, it's the detection of gases involved in life as we know it.
Yes. Yeah, I mean, how do you detect life directly? We can't even decide what life even is. So coming up with a way to detect it directly is very difficult. These are just the contaminants that they would release essentially into the atmosphere that we can then detect and say, hey, maybe this.
Wait a minute, is the oxygen from a tree a contaminant?
I mean, in a way, it's a waste product in a way, right? Photosynthesis produces that.
If you're a tree.
Yeah. I wouldn't think of it that way, but the tree might.
So just remind me, this is 120 light years away. It's a planet discovered from the Kepler mission.
Yeah, Kepler-2. It had a failure after 4 years. It couldn't stare at the same stars anymore, but it could do a second phase of the mission where it looks at the ecliptic plane only. So during that phase, it detected K218.
Just to get the physics of the detection straight. So you've got a star, you've got the exoplanet orbiting the star. Light from the star goes through the atmosphere and comes to you after it's been touched by the gaseous signatures in the atmosphere of the planet.
Contaminated even.
Contaminated. You need the Webb telescope to make this measurement.
Yeah, I mean, you can do it with other telescopes. I mean, Hubble has looked at this before with wide-field camera 3. That's an instrument on there. In that case, they weren't able to detect anything conclusively. And so once JWST came around, everyone was very excited because this is one of the best targets. It's a nice puffy atmosphere around a bright star. It's nearby. So everyone knew this would always be a good planet.
Oh,
to
they
look
knew
at.
that. Okay.
Yeah.
Okay. So what does it mean for a planet to have a puffy atmosphere?
Puffy atmosphere, the 3 ingredients are low surface gravity, ideally. This doesn't really have that, but it's not too bad. You want a hot, warm planet. That's useful because it puffs up the gas.
It heats up the gas,
exactly,
right.
so you get a puffy atmosphere. And you want a light molecular gas because that can go higher in the gravitational well and make a larger atmosphere.
And when you have a puffy atmosphere as it passes in front of the host star, there's more
for us to see.
More for you to see.
Yeah.
And the list of biomarkers, last I checked, is pretty large, even methane. Yet we have lakes of methane on Saturn's moon Titan, but no one's saying it's a place thriving with life. So it's not just the existence of the chemical, it's the conditions under which you expect to find the chemical.
Yes, the context is extremely important. So for instance, with this planet, there is some debate about what the planet really is. One idea is this is an ocean world called a Haitian world. So this is a thin hydrogen atmosphere.
Yes.
And beneath it you have ocean. So there is a surface. Haitian?
Haitian.
Your guess is
Yeah,
yeah, I think it's Haitian.
Okay.
And an important detail here is that if it really was a Haitian world, even having methane alone would basically kind of prove there was life, actually just the methane, because there's no way it should be able to sustain methane in its atmosphere if it really was a Haitian world with this thin atmosphere. It would require a biosphere to make that. I don't know the numbers, but I know from reading my colleagues' papers on this that you would expect there to be parts per million level of methane if there was no life, but this thing has percent level of methane. Whoa. So it has way more than it should do when you do the photochemical calculations.
And what's the best way to get methane from life?
I guess bacteria, probably, I would guess.
So I've always seen methane connected to life that's anaerobic. So like deep in our gut, the microbes there are all anaerobic. And so methane is one of the byproducts.
Right. That's why cows fart methane and we
Yes.
fart methane. Yeah.
What is the only bird that can swim but can't fly? Penguins. By the way, they should rename Antarctica Penguin Land. Penguins everywhere, even on isolated ice floes. They swam there and then they swim back. There's bajillion of them. And they stank. That's worse than if you stink. You stank. And they're so clumsy. They're hilariously clumsy. They're like as high as my kneecap, waddling around, tripping on each other. And I'm realizing, why are they so clumsy? This is embarrassing. What does nature have to say about this? And then I work here at a natural history museum, and I reminded myself they're so clumsy because they have no land predators. That makes them cuter because they'll waddle up to you because they don't think you're going to harm them, and you're not. But if you have no land predators, you don't have to be nimble on the ground because nobody's chasing you. Nobody's ever chased you. I can bet you this, if there's a land predator that showed up, that natural selection would work fast and get the penguins that are not waddling, that are not tripping over their toes. And so that would be an interesting development in the tree of life as a branch of evolution. What would nimble penguins look like? I haven't seen so many penguins. And there are different kinds of penguins, but I'm human, and to me, they all just look like penguins. We never saw the emperor penguin. I'm told they live more inland, less on the coast. It was funny watching them to jump one after another into the water. And then they would chicken out. Can I use the expression chicken out when referring to penguins? Doesn't sound right. A fear factor would descend upon them. Like the penguin in front would say, no, I'm not going to do this. Turn around and walk the other way. Every other penguin in the line gives up on that option after the first penguin decides to not jump. I don't know how they're communicating. Are they spooked? Are they worried that there's like an orca in the water that could eat them, which they do? I don't know, but it was hilarious. I'm just a city kid, so like, what do I know about Drake's Passage? In the body of water between Ushuaia and the tip of the Antarctic Peninsula, that is where the Atlantic Ocean and the Pacific Ocean meet. I don't know if that alone would be sufficient to make it as choppy as it is, or whether there are other prevailing climactic circumstances, but oh my gosh, you see the horizon do this. And you say, well, why is the horizon doing that? No, the boat is doing that. And yeah, so I didn't do much eating during that time. In fact, plates would slide off of the tables. So there's a period of time there where everybody's basically on lockdown to get through Drake's Passage. By the way, our ship is relatively modern. Just in the last 5 years, it's been put on the water. It made me wonder, the explorers from the 19th century, 18th century, when they hit storms, what would that be like? If that kind of turbulence was doing that to our modern ship, I can't imagine what it did to any of those ancient ships that sailed the open seas.
So can we accelerate our time and visit the past?
I think you have to look at it differently. You shouldn't look at it that way. You should look at it as your speed as seen by others. By the way, you don't feel this at all. It's only as measured by others. So if you go fast and time slows down for you, you're still ticking. To you, it's 1 second per second. To everybody else, it's 1 second per 10 minutes, 1 second per hour.
I'm not following it. Explain it. How is it observable by others, my speed?
If I see you, so I'm here and I see you whiz by at some speed.
Okay. You see me walk down the hall.
Well, I was thinking of a rocket ship, but sure.
Okay. All right. A rocket ship.
Okay. Walk down the hall at half the speed of light.
Okay. Which I can do.
All right. I have an equation, a formula that tells me the rate at which your time is ticking relative to me. And I plug it in, and I forgot the number. It might be ticking a third or a fourth.
Well, my time is different than yours because you're stationary and this thing is moving, no?
That's almost the right way to say it. Your time is different from me because we are moving relative to each other. As far as you're concerned, you are stationary, and I'm moving past you at half the speed of light. We don't know. So you will look at me and say, oh, he's moving slow. And I look at you and say, oh, you're moving slow. Both of us will measure the same thing about each other if we are passing each other in the night at half the speed of light.
One going one direction, one going the other.
Correct. And so...
Why is half the speed of light vertical?
It's not. I could say 10%, but it's not linear, so that the faster you go relative to the speed of light, the greater and greater the effects are, all right? So half the speed of light is not half the effects.
Okay.
It's a small fraction, and it grows rapidly.
Okay.
All right? It goes at like the square of your velocity as you get closer. How do I make your time go slower if you're going half the speed of light? I make you go faster. Now you go 3/4 the speed of light, 90% the speed of light. And I can watch you slow down relative to me. Now I speed you up, go slower. Go 1/4 the speed of light, 1/10 the speed of light. How slow can I get your time to go? Stop right in front of me. And that is the slowest we can make your time go.
Which is the same time.
And that happens to match my time, correct.
But
they want to go backwards. We don't know how to do that. Because I have to repeat my time poem.
Please.
If I may.
Please.
We are prisoners of the present, forever transitioning between our inaccessible past and our unknowable future.
Exactly what I say to my wife when she asks if I bought pickles and I forgot.
You're bringing your issues into...
Well, you make it very relatable to my life.
Okay.
And I have a lot of issues. And, I love you, man. I love you. So the answer is...
It's not your fault. It's not your fault.
But there's this obsession in pop culture with this time travel.
We want to go backwards in time.
And do you think, do you just think, and I know, I love you never say absolutes, but like, why? It's dangerous because you start flirting with the past and you alter the future and whatever.
Well, you can flirt with your own future.
So if you went in the past, what would you change?
You have to watch out for that because you don't know the full set of contingencies that would follow.
Okay, who cares about anybody else?
No, they do,
what
because you say, if you go in the past and there's Hitler as a child, will you kill Hitler as a child? would you do that? What you don't know is there's someone else that would rise up that would have been worse than him for the stability of the world in the 1930s and 40s. You don't know that. I'm keeping the past the way it is, not knowing whether having altered it. By the way, this was explored in an episode of Star Trek. They went back in time to the 1930s or late 30s. I forgot the exact year. And Bones, I think it was Bones, the surgeon, falls in love with a woman. You're not supposed to do that because
you're messing with
the time the space-time continuum.
But as usual, men led by their whatever. That's a scientific fact. That is a scientific fact. Go ahead.
No, on that subject, by the way, the first interracial kiss between a black person and white person was on Star Trek, and it was William Shatner.
Oh, I remember that.
It was kissing Lieutenant Uhura.
I remember that.
Okay, they got all kinds of hate mail from the South on that. They could. There's 1967 somewhere around there.
Right.
Meanwhile, Captain Kirk can visit all these galaxies. There's a green woman, a blue woman.
She's got a tumor over here, a horn over here.
He can kiss them. Clearly female aliens.
Yeah.
He's kissing all up in them, but another human who has skin.
He's kissing a woman that looks like a Kreller. That's fine, but not that black woman, damn it. We have standards.
Bones falls in love with this woman.
Yeah.
And she's into peace. She doesn't want war. She sees nations building up, and she tries to prevent the start of the Second World War. This is her motive and her mission. Meanwhile, she gets hit by a bus or a truck and dies, and Bones is distraught. He wants to go back in time again
to prevent
that, to save her. They go back in time again, and that's when Spock does his research. He realizes she has to die, because if she lives, she will successfully delay the entry of the United States into the Second World War, giving Germany, Nazi Germany, the leg up in creating the atom bomb, and they create the atom bomb first and take over the world. And this is communicated to Bones, and the scene where she's going out into the street and the truck is coming, he wants to save her, and and Kirk and they hold him back.
Yeah.
And they just watch her die. Because that's a different world that they don't want to have happen.
Right.
So stay in the present. Get your out of the past.
Okay. That sounds good.
By the way, Hawking has a time travel conjecture where he says he thinks that as we get closer to traveling through time, there'll be some new law of physics that we will discover that will prevent it. And again, you have confidence that when you break matter apart, you didn't break the matter. You're just deconstructing it.
Yeah, it really, I think the way to think about it, when you think about what a collision is, so let's say you collide, as we did in my PhD, electrons and protons together. So you get an electron beam and a proton beam, and you smash them into each other. What's actually happening? What's actually happening is one way that the collision can happen is that the electron can emit a photon, which is a particle of light. And the particle of light goes and it hits the proton. Now, the wavelength of that light, which is telling you how small a thing you can see, is proportional to the energy of the thing. That's how hard we're smashing the things together. So the faster you smash them together, the faster you smash together, the higher the energy, the smaller the wavelength. So the smaller the things that you can see. So that's a way of thinking about particle collisions. So it really is a microscope in that sense. That analogy works.
I'm just thinking, if I were a proton, I wouldn't want to be busted apart into quarks. That would not be a nice day for me.
In some ways, I suppose it's like having an X-ray, I suppose, isn't it? You're right, though. You hit them hard enough and they fall to bits, but that would be the same for you. But we would try not to hit you
except
that hard.
The bits that I fell into, no one's considered them fundamental bits of Neo.
But the other way to think about particle physics, which is, I think, so you say the Higgs particle you mentioned. So that's not in the proton. You're not smashing the things together and finding a Higgs particle buried in there somewhere. The other side is really, so you think about Einstein's famous equation, E equals mc squared. So energy and mass are interchangeable, let's put it like that. So it also says that if we have loads of energy in these collisions, then we can make new particles that are extremely massive, much more massive.
That would come spontaneously out of the available energy that would otherwise be doing nothing.
Yeah, so we have, when you collide protons together at these energies, you have plenty of energy there to make a Higgs particle, for example, or a top quark, which is a very heavy particle as well, far more massive than the protons. So that's, I suppose, the way to think about trying to manufacture Higgs particles so you can observe them. You need enough energy to make them.
So you're not just busting them apart, you're creating an opportunity to view more massive particles than would otherwise be available to you.
Yeah, and the other thing to say, so to get a complete picture, is these very massive things like Higgs particles, they have a very short lifetime. So you make them and they decay away into lighter particles. particles very, very fast. So you don't see the Higgs particle. What you see are the debris from the decay of the Higgs particle. The challenge of particle physics is to detect all those bits that came off, basically. And by the way, you also have the bits of the protons that all got smashed up as well. So it's a big mess. And we have more than...
I've seen these these.
It's very hard because you don't only have one proton collision per... We send the particles around in little bunches, basically. So you can get 10, 20, 30 collisions at the same time. Only one of them on a very good day will be an interesting one. And then so you've got to sift through all this, which is the difficulty or the professional challenge, let's say, of particle physics.
I'd like to offer a perspective that I don't see often shared by people discussing climate change. So, a couple of points. As you surely know, all evidence gathered from many branches of science point to human-induced changes in the climate of Earth since the dawn of the Industrial Revolution. So you've heard that this contributes to the greenhouse effect. And the greenhouse effect is where visible light hits Earth's surface absorbs it, and then re-radiates it in the infrared. And it's that infrared that gets trapped in the atmosphere, raising the temperature. That's the greenhouse effect in a nutshell. When you alter the climate in any way, you are changing what Earth's surface experiences compared with historical averages. So when Earth came out of its last ice age, our nomadic ancestors, trying to not die from a frozen Earth, finally see an Earth that warms up, naturally by the way, but over thousands of years, warm up and become relatively stable. And they say to themselves, this is pretty good, and I'm tired of wandering, and I know how to control crops, and I can control distribution of food, goods, and resources. I'm gonna build a city. Where are you gonna put a city? You're gonna put it on the water's edge, be it ocean, lake, on a river, typically. Why? Oh, because it enables transportation, commerce, irrigation if you have crops. All the greatest cities of the world were built on the water's edge. There is life experience of the records of that city that tell people what is the range of weather that they can experience in snowfall, in rainfall, and in temperature especially. And the city works to accommodate that range.